Our next speaker is Jonathan Hood from here at Harvard. He's going to tell us how to assemble molecules from individual atoms.
Oh, sorry. Yeah, sorry.
Hi, I'm excited to be here at the conference. I am a postdoc in Kansas, and you've already heard from one of our experiments. Oh, thank you. So you heard 2 days ago from Ming Wang about her KRB experiment, where they're observing the reaction complexes in KRB reactions. But today I will be telling you about the other experiment in the lab, which is a sodium-cesium tweezer experiment, where we assemble molecules with optical tweezers. So why optical tweezers? To put this in context, we've already heard a talk yesterday from Lawrence in John Doyle's group where they directly cool molecules into optical tweezers. And we've heard a number of talks where they assemble ultra-cooled molecules starting by first cooling atoms and then doing some type of Feshbach, creating a Feshbach molecule and then a SIRAP to get to the ground state. In this experiment, we are using optical tweezers to first trap the atoms, and then we bring them together and working towards assembling them into the ground state. And so the goal of our experiment is full quantum control of the single molecules, and so that, of course, is the electronic, rotational, vibrational, and in addition, the motional states. But a big advantage that a tweezer array gives you is that we can, once we trap the molecules or the atoms in the tweezers, we can then move the tweezers around in real time. We have single site imaging, so we can detect the presence, make sure that they're there. Here's, for example, a picture of a sodium and a cesium atom, just a few microns apart from each other. And then if we want to study some type of reaction dynamics or collisions, we can merge two tweezers together that, say, have two molecules, and then we can study the reaction where we're just looking at one reaction at a time, and we can precisely control the number and the species of the reactants. So it's kind of the extreme limit of chemical reaction where you're just observing it one at a time. And just to put this in context of some of the physical chemistry experiments that we've seen so far, we can hold the atoms for about 10 seconds, and then we're reaching temperatures that are about roughly 100 nanokelvin, which in terms of inverse centimeter is 10 to the minus 7. So the outline for my talk is I'll first give an overview of our tweezer system, and then I will discuss some very recent, just in the spirit of this conference, some more recent experiments that we've done. One where we fully characterize the sodium-cesium scattering and observe the first Feshbach resonance, as well as first sodium-cesium Feshbach resonance. And then we'll discuss the Raman transfer to a weakly bound molecular state and our progress towards transferring it all the way to the ro-vibrational ground state. So this is just a schematic of how our experiment works. We first trap cesium and a sodium atom in separate optical tweezers, and we cool them. We cool them actually to the motional ground state of the tweezer, and then we merge them together into the same trap. And then once they're in the same trap, we can then perform some type of experiment. We can make a molecule. We can also study the collision of the two atoms. And we had some results from last year, which I actually won't be talking about, where we make excited state molecules. And today I'll be talking more about our preparation of the ground state molecule. So one really nice thing about our experiment is it's actually very simple compared to a lot of the other experiments you've seen. This is our glass cell vacuum chamber. We have a microscope objective right here where we focus down the light into the center. And really the only thing you're missing over here is just like a single ion pump, and that's kind of our whole vacuum chamber. And if you look from this way, you can now see that in the experiment we have some Mott coils around here to make two separate Motts, the sodium and the cesium Mott. This is a picture of a sodium Mott, and you can't see the objective, but it's right here, and it's focusing light down into the Mott, and that's where we can pick out the single atoms. And so in cartoon form, this is what I was just talking about. You have the objective, and you have a glass cell where we have multiple tweezers where we can pick out the single atoms. That light comes from, it's combined together with some dichroics, but both of these tweezers come from acoustic optical deflectors over here. And for people who don't know what that is, it's just a specialized AOM. And when you send in an RF frequency right here, and the angle of the output of the AOD, which gets mapped onto the position of the tweezer, changes as a function of this RF frequency. So by just changing this RF frequency, we can move these tweezers around. And so this is an image of not the atoms, but just two tweezers where we're moving them together. And then what's really nice about this setup is that we can actually, since we use this objective to do diffraction limited tweezers, we can also use this objective to do diffraction limited imaging. And so we just collect the light that's fluoresced from the atoms, we put that onto a CCD, and then we can have very good imaging. This, for example, is a video of a single atom hopping in and out of the trap. And so you can see it's blinking. I mentioned earlier we can hold these for on the order of 10 seconds. Right now it's hopping in and out because there's a Mott surrounding it, and so it's just being knocked out by the atoms in the Mott frequently. And when we do the imaging, if there are no atoms there, and we look at, here's a plot of, for sodium and for cesium, here's a plot of the photoelectron counts on our CCD camera. And for no atoms, we can get a histogram down here. When we have single atoms, then we can get a very good separation between the no atom and the single atom case. You might ask, well, what happens, why don't you see maybe a peak for the two atom case? And the answer is we actually don't see that. It's not really possible because when you shine near resonant light into one of these traps, you get something called light-assisted collisions where pairs of atoms will knock each other out. And so after each experiment, we only have 0 or 1 atoms. And then we can also, very conveniently, if we just send in multiple RF frequencies into this AOD, then that results in multiple traps down here. And so this is a picture from one of our experiments where we have 9 cesium atoms lined up. And we can actually image the atoms and then find where they're missing one and then rearrange it so that we have 100% filling fraction lattice. And so this is work that is related to some earlier work by the Lucan group and Braway's group. So this rearranging is really important, especially for molecules where it guarantees that we'll be able to do 100% filling fraction lattices. So one difficulty in doing an experiment where you have a lattice of atoms or molecules interacting is that in order to get 100% filling fraction, you need to cool them to the quantum degeneracy. And especially for fermions, that's really difficult. And so a big advantage of these tweezers is that you can image, see where you're missing, and then rearrange to get your 100% filling fraction. And I also want to point out another application that we're pursuing, and it was mentioned briefly by Eric Hudson the other day. We have a paper from last year where we kind of outline a scheme for using these optical tweezers to make a very high fidelity quantum gate, where you have two molecules you want to interact. You can use the tweezers to bring them together, use the exchange interaction between the rotational states of the molecules, and then bring them apart. One big advantage of our proposal, what they set out to do in this paper was to make a scheme which it does not depend on having an electric field to polarize the molecules, because electric field control is not something that we have very well and would probably limit the fidelity. So we have a scheme where it does not depend on electric field. We also use states which are insensitive to the magnetic field and the trapping intensity. And so as a result, this scheme is very insensitive to all the expected noise sources that we're going to have. And from just theory, it's just theoretical calculation right now, but we predict a very high fidelity for this type of gate operation. So we have two atoms, and we've trapped them in two separate tweezers. At this point, they're a few microkelvin. I plot here, this is the relative, if we have two atoms in the same trap, this is the relative distance between the atoms. You have the molecular potential, and then up here you have a harmonic potential. It's kind of a difficult thing to plot because these are extremely different scales. You have a molecular potential, which is about 5 angstroms. You have a harmonic potential, which is 1 micron. The separation between these harmonic, the trapping frequencies is on the order of tens of kilohertz, whereas down here we're talking about terahertz. But our goal is going to be to transfer from the ground state of the trap all the way to the ro-vibrational ground state. And we want to do that with extremely high efficiency. And in order to do that, that means we need to cool down all these motional states to the motional ground state, so a single quantum state, because we want to transfer from a single quantum state to another single quantum state. So in order to get 100% efficiency, we're going to need to first cool the atoms down to their motional ground state. Very quickly, because I think we've heard some great ion talks, and it's very common in their experiments, we do, to get to the motional ground state with the atoms, we do Raman sideband cooling. So we start off in some distribution of harmonic states. We have two hyperfine states of the atom. We coherently drive the n to n minus 1 motional sideband. Then we reset by doing spontaneous emission back here. And by doing this, our group has shown for cesium 96% 3D ground state preparation, and for sodium it's roughly 93%. And sodium in particular hadn't been done before, and it was more difficult because it's a lighter atom. It's much more sensitive to the light shifts, and we actually need to switch off the cooling light and the trapping light. They can't be on at the same time. And it's also outside the lambda regime, so we have a paper from last year, and then we have a paper that was just accepted for cesium. And finally, so we have two atoms. They are now in the ground state of the separate the separate traps, but now we want to merge them together. And so we have two different wavelengths for the atoms, and you could, in principle, use the same wavelength for both atoms, but the thing is that once we merge them together, after we perform an experiment, we actually would like to separate them so that we can then image them and see if they're still there. And so we've learned the way to do this is that you need to use two different wavelengths so that the atoms, in this case we use one wavelength which is actually trapping for sodium, the 700 nanometers, but anti-trapping for cesium. And so if you look at this in term, this is what the potential would look like for sodium as a function of time, going from the tweezers separate to the tweezers together, and you can see that the sodium atom in this case is not moving, and it gets mapped here. And then you have the case for cesium, where cesium, you can see cesium is actually anti-trap of the sodium, but in this case it's actually adiabatically mapped to the ground state of this trap. And we've learned that it takes a specific combination of wavelengths and powers. For example, here's a plot of the cesium tweezer power and the sodium tweezer power, and there's this window where everything works well. You can see this line right here for a specific cesium tweezer power where we get very low ground state fraction. Turns out this is unfortunate consequence of using AODs. When you use AODs and you're moving the atoms along, there's these acoustic standing waves in the AODs, and that actually modulates your trap very little, and you're like less than on the order of 1%, but that still results in a lot of heating out of the ground state. So you just have to, the companies won't actually tell you how much it modulates. They're not that aware of this problem, so you just have to get a lot of different AODs and test them out to find ones that have small modulation. So now we have both atoms, and they're in the motional ground state of a single tweezer. I will get back to preparing the weakly bound molecule and then the progress towards the ro-vibrational ground state. But I first want to discuss something that we've done just in the last couple months in collaboration with theorist Bo Gao. And we wanted to characterize the scattering properties of sodium cesium. And we set out to answer the question, what is the least number of parameters that we can have to fully characterize the interactions of sodium and cesium over a certain energy range? And so we're learning that for large systems, the coupled channel model calculations are becoming very difficult. And so it becomes necessary to create some type of effective theory that can explain the interactions that doesn't necessarily need to contain all of the short-range details. And so Bo works with multi-channel quantum defect theory, and we set out to answer the question, what is the simplest way to characterize all these interactions in these tweezers? And what we ended up doing was just actually measuring the shifts of the tweezer trapping frequencies due to the collisions. And so I'll explain what this means. So we have this molecular potential, we have the harmonic potential, and so this is a function of the distance between the two atoms. And then what we're going to do, just to simplify this, is we're going to ignore all these details and replace it with just a delta function. This is very common. This is a Fermi pseudopotential. And then if we look, so we have two particles in this harmonic trap, but if you switch to the relative coordinates, you can think of this just as one particle in a harmonic trap. And so it just becomes a one particle problem. And here are the harmonic wave functions. This interaction between the two atoms is just represented by this delta function here. And you can see from this that there are some states that are interacting, where they see the delta function, the wave function sees the delta function, there's interacting, and then you have other states that don't see it. So there's going to be a set of interacting and non-interacting states, and all of the interacting ones will be shifted by this interaction, by this delta function, and we're going to measure these shifts. And so now I'm giving the real answer, which is here I'm giving the calculation of all the trapping frequencies as a function of the scattering length, where I'm just normalizing the scattering length by the oscillator length. And first, just take a look at the case of 0, which is when the atoms don't interact at all. So this is just two independent atoms in the tweezer. You have the motional ground state, and then, for example, you have a single excitation in one atom, a single excitation in the other atom, and then you have a set of 3 here, 2 excitations in one atom, 2 in the other, and then 1 in each. And then as the scattering length changes, you can get shifts in these trapping frequencies. And what we do in the experiment is we just do a Raman transition where we switch between two different spin states, two different ground spin states, hyperfine states, and we can say go from this scattering length in this particular measurement, we go from a hyperfine state that has a very small scattering length to another one, which has a larger one, and then we can observe the shifts of these peaks. And so, for example, this red curve right here is when we drive this hyperfine transition without the second atom there. So this is just a single atom hyperfine transition, and we only see one peak. But then if we repeat this process with the other atom there, so we flip it spin with the other atom there, we see that the main peak shifts over, and this shift is just corresponding to the shift going here, from this line to this pink line here that I drew. And so we can, by measuring these interaction shifts, we can figure out what the scattering lengths are of each of these hyperfine state components. And what's was interesting to us is that you see a few other peaks here. We have, due to selection rules where the position wave functions have to be, cannot be orthogonal, we can actually only drive to states that have the same center of mass coordinate. And so in this case, we can actually only drive to this state, and we can drive to this particular state here, which is one that's also interacting, but has the center of mass quantum number, which is the same as the initial one. and that corresponds to this peak right here. So, and then there's additional excited states that we mod. And then there is a peak at the center here, the zero frequency shift. And if you can look at this, we're going from here to there. There's actually no line there. So what this ends up corresponding to is that we don't actually start fully in the 3D quantum ground state. So we actually start off with a little bit of the atoms in some non-interacting states up here. And so when we drive from a hyperfine state corresponding to this scattering length to a hyperfine state corresponding to this oscillator scattering length, then we get some of the atoms in the non-interacting states just get mapped to the same state. And so we can actually figure out how much is in the 3D quantum ground state from this. And so we give these numbers to Bo. We also do a measurement of the binding energy of a particular state, the triplet state, and then we can extract what the triplet and singlet scattering lengths are. We also do spectroscopy of a rotational excited state of the least bound molecular state, and we can get the C6 coefficient, which agrees fairly well with theory. And then from this MQDT model, we can actually then predict what the scattering properties will be over a large range of magnetic fields. So in this case, we have a small magnetic field. But from this model, we can predict where the Feshbach resonances are going to be. And so we have a version, we call it version 1.5 of the experiment, where we have the same glass cell and optical tweezers, but now in this case, we have these very large Feshbach coils to make magnetic fields up to a Tesla, roughly. Sorry, 1,000 Gauss. And then, very different. And then we observed, from the model, they predicted two Feshbach resonances for sodium Cs, unfortunately at very high magnetic fields, which is why I'll explain in a little bit a technique we were trying to do in order to avoid using these Feshbach resonances. But we've observed these Feshbach resonances, and the first sodium cesium Feshbach resonance, and also first an optical tweezer. And they agree with this MQDT model just based on these simple measurements we've done with 1% accuracy, which we were kind of surprised with. And so now I'm going to switch back to this picture of the story of creating the weakly bound molecules and then ro-vibrational ground state. So this has now been done in a number of molecules. The general scheme that people have used so far is you start off in some free atom case. In our case, it's actually a trap state. You want to transfer all the way down to the ro-vibrational ground state. It's very difficult to do that because of the Frank-Conen factors going from a very loosely bound state to this very tight state. And so what people have done is they have created a loosely bound molecule using Feshbach resonances. And so we've now observed Feshbach resonance, so we can pursue this. But for a while, we were trying to figure out if there was a way to do this without relying on the Feshbach resonance. And so can we transfer from this trap ground state to a loosely bound molecule all optically without using a large magnetic field? This is convenient, for example, in this atom where the Feshbach resonances are very high magnetic fields. But there are also some other molecules that don't really have Feshbach resonances that are well suited for doing magnetoassociation or RF association. For example, alkali plus alkaline earth have very narrow Feshbach resonances. Not sure there's going to work yet. So we set out to see if this all-optical transfer to a loosely bound state would work. And the scheme is shown here. We have a trap state. We have a weakly bound molecule, which is detuned by a couple hundred megahertz. And then we just want to do a Raman transfer. And so it's a very simple conceptually. And then we have some excited state that we're using as the intermediate state. We have a detuning from this. And so just in a Raman transition, you have an effective Rabi frequency from going here to there. And it's a function of this detuning, so you want to detune really far. Why this ends up being a little bit more difficult, there's two reasons actually, than typical Raman transitions, is that we have, so first of all, when you're doing a Raman transition, the number of scattered photons that you get during a pi time is related to two factors. One, you have a excited state decay, and then you have a detuning, and so you want to go detune as large as possible. And the second factor, which is difficult for us, is you have a ratio between the omega 2 and the omega 1. And that actually hurts us a lot because we're going from a trap state to an excited, very, very tightly confined molecular state. And so this Frank-Conen factor is 10 to the minus 9. It's very small. And the one going down is 10 to the minus 4. So this alone, we could just say, oh, we'll just attune very, very far away. But the other problem in this type of transfer is that you have these near threshold states at the top. And these near threshold trap states and this weakly bound states essentially have a Frank-Conen factor of unity 1 with this. And so you get very high scattering with this near threshold states. And that sets an overall limit for the time scale when doing this Raman transfer. And so what we actually do to overcome this is we use the tweezer itself as the Raman light, because we want as intense Raman light as possible, because we know that the tweezer is going to be scattering off these near threshold states. So we use the tweezer as the Raman light. We just use an AUM to separate the two frequencies and then drive this transition. And from the calculation, from including all these levels, the full calculation, they expect about a 1% loss when doing a transfer from here to here, which we were very optimistic about. And we have observed the Raman transfer signal, and we can, from the models right now, we estimate that we can transfer about 70% of the atoms here. The problem is that the line widths that we get are much, much broader than the theoretical model predicts. And we can do measurements with, so this is the Raman transition. It gives us the binding energy from here to here of approximately 300 megahertz. And we can track this Raman transition as a function of its detuning and the power and map out really carefully with this omega 1 and this omega 2. They agree very well with the theoretical prediction. But as the formula I gave earlier is that this number of scattered photons during a pi time is proportional to this lifetime. And the problem is that for some reason, which is unclear, it's about 100 times larger than what theory predicts. And so people who work with molecules, the line width of this is expected to be about 5 megahertz. We're measuring something more like a gigahertz. And so it's unclear now why this line width is so broad. It seems that this line width, we've done spectroscopy directly in line width by just scanning over it, and it seems like the line width the broadening might have something to do with the fact that we have a tweezer very close to it. When we tune the tweezer very far away and then probe it with weak light, we get a much narrower line width. So we're doing some investigations on what's causing this broadening. And so then after we transfer to this loosely bound state, the next step will be STIRAP, which has been done many times. We have everything set up for it. So that is the end of my talk. And just in summary, we prepared sodium cesium atom and the ground state of optical tweezers. We can perform some simple experiments where we study the collisions, create excited molecules with the sodium cesium, and then we transfer to weakly bound states, and we're making progress towards getting to the ro-vibrational ground state. And that's going to thank my group. So there's the two versions of the experiments, one with the we call 1.0, which is I labeled the people at the top, and then there's this next generation which has the Feshbach coils, and I labeled the people on the bottom on that experiment. So thank you.
Questions?
Sorry, I was a bit confused. You say as you make the Rabi frequency 1 larger, make that light more intense, you scatter fewer photons?
Sorry, say it again?
That's the formula, yeah, the expression.
As you make this one larger?
Yeah, you scatter fewer photons.
Yes, and so there is the Rabi Raman rate, so just whenever that gives you the pi time, and then there's a scattering rate. In this case, the scattering rate is coming really just from this transition coupling to this state. It's because this is extremely weakly coupled to this state because it's a trapped state. The Frank-Kohn effect here is much larger, and so the scattering rate goes with omega 2 squared. And so when you multiply your pi time times your scattering rate, you get a ratio of omega 2 over omega 1. And so the closer omega 2 is to omega 1, the less scattering you have. And so the ratio for us is 300, so that means we're actually 300 times worse than what you would get if they were equal.
If your goal is to have an array of dipole molecules, isn't going with directly laser coolable dipolar molecule simpler than just associating them?
Well, I guess you could conceptually, it might be simpler, but these experiments are very technically challenging to directly cool laser molecules. I've just been working in the last few years, and so assembly is a molecular assembly was demonstrated first in 2008. It's worked for a number of molecules. It's actually a little bit more straightforward. The experiment is simpler in that case, and so as we learn to directly cool more molecules, I think it will. Yeah.
Common pointer I would say, one of the things is that different kinds of molecules are useful for different applications, including the quantum simulation, metrology, these kinds of things. So regardless of anybody's particular opinion of the difficulty of any particular experiment, having this breadth of techniques and the breadth of molecules, I think, is extremely important for the field. And so there are some molecules, like the ones you're working with which can't be directly laser cooled, at least not easily. So it's one possible answer.
Right, so I guess we really treat these as complementary approaches because the challenges are very different. So in this case, by design, once we reach there, it's full quantum state control, including emotional control. In the laser cool case, right now it's 50 meters problem. So the emotional, if you want one emotional ground state, that needs to be further cooled, which hasn't really been looked at. But certainly on the list to do, just haven't had the time.
May I add? So I guess you have a list of pros and cons, and there's state preparation and state detection that might be already have a clear path for the laser coolable molecule.
So how to detect the molecules?
Yeah, and for the associating molecule, maybe it's not so clear how to do the detection, but both approaches are trying to reach the same goal, like controlling the emotional state.
Yeah.
And get the state detection, state preparation worked out.
Yeah.
That's
Yeah, so for state detection, there's a few, once we have molecules, there's a few strategies. One could be to, if this association of the molecules, of the atoms to the molecule is very high efficiency, what we expect the SIRAP is typically close to 100%. If we can get the Raman transfer or magnetic association, whichever one we end up doing, to close to 100%, then you can actually just separate the molecule and then detect the atoms as a way to detect whether the molecule there. The other strategy, which is similar to calcium fluoride, is that there are excited states that have a very high Frank-Kohn factor from the ro-vibrational ground state, and so we could imagine just scattering photons and then doing direct imaging of the molecule itself.
We maybe have time for one more very quick question.
So do you speculate what is the reason for this broad resonance that is much broader than theory?
Yeah, so we have been talking a little bit with Olivier about this to try to figure it out. Initially, he had three ideas. One would be that it's a C triplet sigma v equals 0 state that we've been using. It could be coupled weakly to some dissociative state. There's not the dissociative state in this case would actually be a triplet ground state that comes up and then has an avoided crossing, which has been theoretically predicted but never observed. So that's one possibility. It kind of disagrees with our experiment a little bit at this point, but we're still doing measurements. The other one is that it could be a 2-photon transition to some excited molecular potential. But we are doing now experiments. We are scanning different vibration levels of the C triplet sigma. We're also moving the tweezer around to see how it depends. It seems like at this point that it depends on the tweezer position, this very intense tweezer position, so kind of points to it being some type of two-photon process, but it's not clear yet.
All right, so we have a break now, and we're back at 10. Thank Jonathan again.